The tap rule in National Electrical Code section 240.21b allows a tap conductor to be connected to a busbar or conductor at any point along its length. In this specific scenario, a new 2500 amp feeder is proposed to be connected to the busbar of an existing 4000 amp service board. The question is whether this connection is permissible under the tap rule. To determine this, we must examine the conditions outlined in section 240.21b of the National Electrical Code. Firstly, the tap conductor, which is the 2500 amp feeder in this case, must not exceed 25% of the ampacity of the busbar it is being connected to. In this instance, the busbar has an ampacity of 4000 amps. 25% of 4000 amps is 1000 amps. Because 2500 amps exceeds 1000 amps, it fails this part of the tap rule. Secondly, the tap conductor must be protected by an overcurrent device. This means that the 2500 amp feeder must have a 2500 amp main breaker in the new 2500 amp board to which it is feeding. This condition is met assuming the installation adheres to this design. Thirdly, the tap must be made directly to the busbar and not to a branch circuit or other load. This condition appears to be satisfied, as the description indicates a direct connection to the busbar. The fact that the 4000 amp service board is the main service board does not, in itself, invalidate the application of the tap rule. The tap rule applies to any busbar or conductor, regardless of its location within the electrical system, provided that all other conditions are met. However, in this specific case, the first condition is not met because the 2500 amp tap conductor exceeds 25% of the 4000 amp busbar ampacity. Therefore, based on the information provided, it is not permissible to connect the new 2500 amp feeder directly to the busbar of the 4000 amp service board using the specific interpretation of the tap rule because the tap conductor exceeds the 25% threshold. If the tap conductor was instead 1000 amps or less, it would be allowed to proceed. It's essential to consult with a qualified electrical engineer and local electrical inspectors to ensure compliance with all applicable codes and regulations before undertaking any electrical work. This is crucial because the interpretation and enforcement of electrical codes can vary depending on the jurisdiction. Also, other factors not explicitly mentioned, such as the specific type of overcurrent protection and the physical installation methods, could affect the overall compliance of the installation. In addition to the general conditions of section 240.21b, it is important to consider other relevant sections of the National Electrical Code that may apply to this specific installation. For example, section 230.95, which pertains to ground fault protection of equipment, may be relevant if the service is rated 1000 amps or more. This section requires ground fault protection to be provided for each service disconnecting means rated 1000 amps or more. If the addition of the 2500 amp feeder causes the overall service to exceed this threshold, ground fault protection may need to be added or upgraded. Furthermore, section 110.9, which addresses interrupting rating, is crucial to consider. All electrical equipment must have an interrupting rating sufficient for the available fault current at its terminals. The addition of the 2500 amp feeder may increase the available fault current at the 4000 amp service board, potentially necessitating an upgrade to equipment with a higher interrupting rating. Another important consideration is the load calculation mentioned. A thorough load calculation is essential to ensure that the existing service has sufficient capacity to handle the additional load of the 2500 amp feeder. This calculation should take into account all existing loads, as well as any future loads that may be added. It should also consider demand factors, which allow for the fact that not all loads will be operating at their maximum capacity simultaneously. It is also essential to ensure that the physical installation of the tap complies with all applicable requirements of the National Electrical Code. For example, the tap conductors must be of sufficient size to carry the intended load, and they must be properly protected from physical damage. The connection of the tap conductors to the busbar must also be made in a workmanlike manner and in accordance with the manufacturer's instructions. In summary, While the tap rule in Section 240.21b of the National Electrical Code may seem applicable at first glance, a closer examination reveals that the 2500 amp feeder exceeds the 25% threshold. Additionally, it is important to consider other relevant sections of the National Electrical Code, such as those pertaining to ground fault protection, interrupting rating, load calculations, and physical installation. Consulting with qualified professionals and adhering to all applicable codes and regulations are essential to ensure a safe and compliant electrical installation. When considering tap rules and their application to electrical systems, it is also crucial to understand the different types of tap rules that exist within the National Electrical Code. Section 240.21 outlines several different tap rules, each with its own specific requirements and limitations. These rules are designed to provide flexibility in the design and installation of electrical systems while maintaining a high level of safety. The tap rule discussed so far, found in Section 240.21b, is specifically for feeder taps. However, other tap rules exist for different types of circuits, such as branch circuits. It is essential to correctly identify the type of circuit involved in order to apply the appropriate tap rule. For example, Section 240.21c covers tap rules for branch circuits. These rules typically have more stringent requirements than the feeder tap rules, reflecting the higher risk associated with branch circuits. Branch circuits are closer to the point of utilization and therefore more likely to be overloaded or subjected to faults. In addition to the specific requirements outlined in Section 240.21, it is also important to consider the general requirements for overcurrent protection found in Article 240 of the National Electrical Code. This article provides comprehensive guidance on the selection and installation of overcurrent protective devices, such as fuses and circuit breakers. The overcurrent protective devices must be properly sized and coordinated to protect the conductors and equipment they serve. They must also be readily accessible and properly labeled. Furthermore, it is crucial to consider the impact of voltage drop on the performance of the electrical system. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the source. This can be caused by the resistance of the conductor and the amount of current flowing through it. Excessive voltage drop can lead to a variety of problems, such as reduced equipment performance, overheating of conductors, and nuisance stripping of overcurrent protective devices. To minimize voltage drop, it is important to select conductors of sufficient size and to keep the length of the conductors as short as possible. Voltage drop calculation should be performed to ensure that the voltage at the end of each circuit is within acceptable limits. In the context of the 2500 amp feeder installation, voltage drop could be a significant concern due to the high current and potentially long conductor run. It is important to carefully consider the conductor size and length to ensure that voltage drop is within acceptable limits. Another factor to consider is the ambient temperature in which the conductors will be installed. The ampacity of a conductor is affected by the ambient temperature. As the ambient temperature increases, the ampacity of the conductor decreases. This is because the conductor generates heat as current flows through it, and the higher the ambient temperature, the less heat the conductor can dissipate. To account for the effect of ambient temperature, correction factors must be applied to the ampacity of the conductor. These correction factors are provided in the National Electrical Code. In the 2500 amp feeder installation, it is important to determine the maximum ambient temperature in which the conductors will be installed and to apply the appropriate correction factors to the ampacity of the conductors. If the conductors are installed in a hot environment, it may be necessary to increase the size of the conductors to compensate for the reduced ampacity. Furthermore, it is essential to consider the type of insulation used in the conductors. Different types of insulation have different temperature ratings. The temperature rating of the insulation indicates the maximum temperature at which the conductor can operate safely. It is important to select conductors with insulation that is appropriate for the operating temperature of the circuit. The National Electrical Code provides tables that list the temperature ratings of different types of insulation. In the 2500 amp feeder installation, it is important to select conductors with insulation that is rated for the maximum operating temperature of the circuit. This will help to ensure that the conductors do not overheat and that the insulation does not break down. In addition to these technical considerations, it is also important to consider the practical aspects of the installation. The conductors must be properly supported and secured to prevent them from sagging or becoming damaged. The connections must be made in a workmanlike manner and must be properly tightened to ensure a good electrical connection. The equipment must be properly grounded to provide a path for fault current to flow back to the source. A thorough inspection should be performed after the installation is complete to ensure that all work has been performed in accordance with the National Electrical Code and other applicable standards. This inspection should be performed by a qualified electrical inspector. The inspection should verify that all conductors are properly sized, that all connections are properly made, that all equipment is properly grounded, and that all overcurrent protective devices are properly sized and coordinated. Any deficiencies that are identified during the inspection should be corrected before the electrical system is energized. By carefully considering all of these factors, it is possible to design and install a safe and reliable 2500 amp feeder installation. However, it is important to remember that electrical work can be dangerous, and it should only be performed by qualified individuals who are familiar with the National Electrical Code and other applicable standards. It is always best to consult with a qualified electrical engineer or contractor before undertaking any electrical work. They can provide expert guidance and ensure that the installation is performed safely and in accordance with all applicable codes and regulations. When discussing the tap rule and its application, it's also important to address common misconceptions and potential pitfalls. One common misconception is that the tap rule allows for unlimited flexibility in the design of electrical systems. While the tap rule does provide some flexibility, it is important to remember that it is subject to certain limitations and requirements. The tap rule should not be used as a substitute for good engineering practices or for thorough understanding of the National Electrical Code. Another potential pitfall is the failure to properly coordinate overcurrent protective devices. Overcurrent protective devices must be properly sized and coordinated to protect the conductors and equipment they serve. If the overcurrent protective devices are not properly coordinated, it can lead to nuisance tripping, which can disrupt the operation of the electrical system. It can also lead to damage to equipment and even fire. To avoid these problems, it is important to perform a coordination study to ensure that the overcurrent protective devices are properly sized and coordinated. A coordination study is a detailed analysis of the electrical system that takes into account the characteristics of the conductor's equipment and overcurrent protective devices. The coordination study will identify any potential coordination problems and will recommend solutions to address them. Another important consideration is the potential for harmonics in the electrical system. Harmonics are currents and voltages that are frequencies that are multiples of the fundamental frequency. Harmonics can be caused by a variety of nonlinear loads such as electronic ballasts, variable frequency drives, and computers. Harmonics can cause a variety of problems such as overheating of conductors and equipment, reduced power factor, and interference with communication systems. To mitigate the effects of harmonics, it is important to use harmonic filters. Harmonic filters are devices that are designed to block or reduce the flow of harmonic currents. Harmonic filters can be installed at the source of the harmonics or a point of common coupling. In the 2500 amp feeder installation, it is important to consider the potential for harmonics and to take steps to mitigate their effects. This may involve using harmonic filters or other harmonic mitigation techniques. Furthermore, it is essential to consider the impact of the installation on the overall reliability of the electrical system. The electrical system should be designed to be as reliable as possible. This means that it should be able to withstand faults and other disturbances without causing a major outage. To improve the reliability of the electrical system, it is important to use redundant components. Redundant components are components that are installed in parallel so that if one component fails, the other component can take over. For example, redundant power supplies can be used to ensure that a critical load is always powered. In the 2500 amp feeder installation, it may be desirable to use redundant feeders to improve the reliability of the electrical system. This would involve installing two feeders in parallel so that if one feeder fails, the other feeder can take over. In addition to these design considerations, it is also important to consider the maintenance requirements of the electrical system. The electrical system should be regularly inspected and maintained to ensure that it is operating properly. This includes inspecting the conductors, equipment, and overcurrent protective devices. It also includes testing the overcurrent protective devices to ensure that they are operating properly. A preventive maintenance program should be established to ensure that all necessary maintenance is performed on a regular basis. This will help to prevent problems and to extend the life of the electrical system. In the 2500 amp feeder installation, it is important to establish a preventive maintenance program to ensure that the electrical system is operating properly. This program should include regular inspections, testing, and maintenance of all components of the electrical system. By following these guidelines, it is possible to design, install, and maintain a safe and reliable 2500 amp feeder installation. However, it is important to remember that electrical work can be dangerous, and it should only be performed by qualified individuals who are familiar with the National Electrical Code and other applicable standards. It is always best to consult with a qualified electrical engineer or contractor before undertaking any electrical work. In conclusion, while the initial assessment based on a simplified interpretation of Section 240.21b might lead to the incorrect conclusion, a comprehensive understanding of the TAP rules and related code sections, combined with careful consideration of factors like overcurrent protection, voltage drop, ambient temperature, harmonics, reliability, and maintenance, is crucial for a safe and compliant electrical installation. The 25% rule is critical, and any misapplication can lead to potential hazards. Always consult with qualified professionals to ensure that all aspects of the installation meet the necessary standards and regulations.